So is my screen visible?
Yes, sir, it is visible.
Okay, okay, great, great. Okay, so let us continue from where we left yesterday evening. We were so a quick recap. We started with Deutsch algorithm. We saw that this is one of those first theoretical algorithm. At that time, it was theoretical analysis was done, which proved that yes, you can gain some sort of quantum advantage without using a classical algorithm. And we also saw that in classical you will require two steps, but in Deutsch algorithm you will require only one step because of the principle of quantum parallelism, which essentially means superposition. And then we saw several of these oracles, which we told that these oracles have the power for a balanced or a constant function. And we said that in Deutsch algorithm we also try to find whether the encoded function, unknown function in the oracle is a constant or a balanced function. Then we saw the steps of the Deutsch algorithm, where we first apply Hadamard gates to both the qubits. The qubits are started in ket 0 and ket 1. Then we apply the unknown oracle. Then we apply Hadamard gate to the first qubit without doing anything to the second qubit. And finally, we make a measurement on the first qubit. Now let us, and also we started with the analysis of the Deutsch algorithm's quantum circuit. So if you see, we have started the analysis for that, and we saw the circuit also, where we start with the gate 0, and then we move, we apply Hadamard gate, then we defined it into several steps, and now we are solving step by step. So we have solved step 0, step 1, where in step 0 we initially prepare the state get 0, get 1. Then in step 1 we also have applied Hadamard gates, and now we are going to see step 2, where now we are going to apply the oracle. So let us see, let us apply the oracle. So let us go to step 2. So step 2 is applying the oracle uf to the above state. Okay, and the above state, what is the above state? Which is ket phi 1, right? And ket phi 1 is a superposition state, which after applying the Hadamard, right? So that is a superposition state. So now onto this superposition, this oracle will be applied. That means this oracle will be simultaneously applied to all the states, but we are going to do the computations like one by one to showcase how it is being applied, okay, for our better understanding. So we apply the oracle uf to get phi 1. This is the part of quantum parallelism. This is the part of quantum parallelism. So apply this. So apply uf to each term. So as I mentioned, since this is a superposition state, each term will get the uf application. The unitary will be applied to each of these quantum states. Then what is the result? What we are going to get? Let us see one by one. We will apply one by one. Now recall this. So I have taught you this yesterday. So recall from your the notes which you have taken in the evening, yesterday evening. So uf, okay, we are going to use this formula. Okay, uf, you will find this in your steps, okay, where you wrote your steps. Uf xy, the inputs, gives you the outputs as follows, and we are going to use this. Okay, we are going to use this formula, because this is the formula of the oracle. Okay, you can say that this is the formula. Okay, this is the formula. You can note this down. Formula of the oracle. Okay, formula of the oracle. This is a generalized, okay, generalized formula. generalized. Okay, and now we are going to use this formula of the oracle to derive how what will be the outputs, which outputs we are going to get when the UF is applied to each of the quantum states, ket 0 0, then minus ket 0 1, then ket 1 0, ket 1 1. So let us start applying. So UF, so I will just make a dot. This is like a bullet point dot UF applied to ket 0 0. So let us apply them and let us write the formula. Okay, xy, right? So we are going to have xy. Okay, xy and then 0. That means x and 0 XOR 0 XOR f of 0. So basically, like, there's the same one. So y XOR f of x, where x is 0, right? So just using the above formula. Okay, I'm not going to write it again and again. This is the first step, that's why I wrote it. But you can, like, easily apply. Okay, this is not very difficult, very easy only. And then under this we will have two conditions. What are those two conditions? We can have two, the input is same. Okay, the input is same, fx, x is the input here, so we have taken x as the input, so and y as the supporting qubit. So x is same, the input is same, but for the same input we could have different outputs. So what are the possible values? 0 and 1. So we are going to check it for both the results. So if f of 0 is equal to 0, okay, if f of 0 is equal to 0, then what will happen? Then you need to start calculating now. Okay, so again, like, apply the formula. Okay, if you have forgotten how the XOR operation looks like, so maybe I can just write it down. Okay, okay, so whenever you have qubits 1 0 1 1, okay, and whenever you take XOR of them, okay, whenever you have XOR of them with each other, then what will you get? 0. Here you will get 1, here you will get 1 0. So basically, when both the bits are same, you get 0 result. Only when they are different, then only you get one result. That is exclusive OR, right? That is the meaning of exclusive OR. Okay, that's why it's a OR, but a exclusive OR. Okay, it's a little bit different kind of OR. Okay, exclusive OR, that's why we call it. So therefore you need to apply that, and once we apply that, UF to ket 0 0, and once you solve that, you are going to get ket 0 0. Okay, you can easily solve it for f of 0. Like, for f of 0 we have taken it to be 0 here, therefore just put this value here on this top in this formula. Okay, in this formula you need to put the value. F of 0 is 0, and then 0 XOR 0 is 0. So you will get 0 comma 0, right? So UF of 0 0 becomes 0 comma 0, that means 0 0. So that is how I am writing it. And mathematically, another way of writing that is with a coefficient. So 1 minus f of 0 times ket 0 0. This is another way of writing mathematically, right? Mathematically, what do we do mathematically? What is, whenever you study mathematics, okay, whenever you study mathematics from your, I'm saying, like, about many years back, like from your childhood, what do you do in mathematics? What is the basic principle? You try to see things from a different perspective, right? You always see that can we write some result in some other format or not, right? I mean, if you see the whole mathematics, whether you take abstract algebra, whether you take higher advanced calculus, or whether you take any optimization, you can take anything. Okay, you will always see that we can, when we get a result, we try to write it in some other convenient way, right? And then later we can find out that, okay, if we write it in that particular format, then we can get a result in a different format, or we can derive a particular formula, right? That is you can understand, right, what I'm trying to say. In mathematics you try to see things from a different perspective, right? Whenever you get a result, you can try to write it in some other format, right? So this is what I'm doing. Okay, you have ket 0 0, but I'm writing 1 minus f 0, which will also give you the result 1 only. And then because f of 0 is 0, right? So therefore 1 minus 0 is what? 1. So 1 multiplied by ket 0 0 is ket 0 0. So therefore you can see that it indeed validates. So it's a different way of writing. And why do we write things in a different way? You can ask this reason. Why do we do it in general only? I'm not saying about quantum, but like, whenever you study any subject related to mathematics, you will write things in different way. Why? To derive different results, right? And those different results have different applications. That's why you try to write it in a different way, right? That is a sense, right? I mean, like, we study maths, okay, but sometimes we do not try to realize these things, and you should definitely realize these things. Even while doing research, we do not realize, okay. So that is why I'm emphasizing this fact, because students are also there. Always whenever you are doing maths, you see that you are trying to write things from a different perspective. You try to write down some other kind of equation from the first equation which you derived, okay. Why? Because that kind of notation which you are writing, the current notation, it could have a different functionality, it could have a different application. You can apply it and you can compare it with some other concept, right? So therefore it also helps building an interdisciplinary conceptual nature as well, right? So that is why writing in different ways is a thing, it is a like an inherent technique in maths, you can say, okay. And similarly, if f of 0 is equal to 1, then also you are going to have uf ket 0 0 is equal to 0 1, right? Because now it is f of 0 is 1. So again, put it in this formula, above formula here, which I have underlined, okay. So just 0 XORed with f of 0 is 1. So 0 XORed 1 is 1, right? You can consider this. If you have forgotten XOR operation, you can consider this. And again, like, you can write it in a different form. Now since f of 0 is 1, so therefore you can only write it as a f of 0 and 0 1, okay. Because f of 0 is 1, and 1 into ket 0 1 is ket 0 1, right? So again, like, different ways of writing. And this is going to be useful, okay. That's why we are writing like this. In the end, you will see that we are able to apply the technique of quantum interference to gain our measurement result, okay. That's why I'm writing like this format, okay. Initially, when the results are derived, you might not write in this format, but like, whenever you want to derive a particular result, then you have to again, like, go back and look at the things from a different perspective, right? This happens a lot in research also, right? We derive something, okay, and then we see that, okay, we are getting this result. Can we make it a bit more efficient? Then we rewrite it in some different format, right? Like, it's like solving algorithm. Like, for example, you have some algorithm to solve a list of elements in a stack or a queue or something, let's say. And then, like, you derive one algorithm for it, and then later on you also optimize it, right? This is what is done in Google and all these big companies interviews, right? You need to derive an algorithm, you calculate its time and space complexity, and then you resolve it again in a different format where you can improve the time and space complexity. This is what is done, right, in the big companies. This is what is asked in interviews. Actually, most of the interviews are based on this only. Okay, so you can also consider, this is not the same thing, but yes, it's like a similar kind of analogy I'm trying to make, where you have different way of writing things. So therefore, uf 0 0 ket 0 0, therefore we get this result, 1 minus f of 0 ket 0 0 plus f of 0 ket 0 1. So you just take them together, that's it. So this is the uf of ket 0 0. Okay, now we are going to apply uf to ket 0 1. So what are we doing? Actually, we are applying to these states, right? The states which we have derived, right? So the uf of this is done, okay. Ket 0 0 is done, okay. Now we are going to apply to this one, okay, ket 0 1. Okay, so let us apply to ket 0 1, uf of ket 0 1. Now I'm not going to write x y x y x or fx, not going to write them again and again, but it is understood now, okay, how you are applying the formula. So 0 comma 1 XORed with, because y is 1, right? So x and y, okay, y is 1, right? So therefore y XORed with f of x, okay, x is 0 still, so f of 0, okay. So very easy, right? I mean, you can, if you know the XOR operation, then I mean, very easy. This is not very, this is not hard. The only thing is that the computation is a little bit longer. That's it. So that's why I didn't covered it yesterday. And after this, we are going to see the Qiskit implementation also. Okay, so and then what will happen? So now, like, you can without my help, actually, you can start solving by yourself also in your notes. Okay, and I highly recommend that you do that, because now it's very easy. And again, we can write it f of 0, 0, 1. Okay, very easy, right? Just applying the XOR operation. So once you know one step, the other steps are very easy. And similarly, if f of 0 is equal to 1, then again the same thing. This is the same thing now will repeat for all the states. Okay, ket 0 0, ket 0 1 is done, then ket 1 0 and ket 1 1. So you can solve it, you can start solving it by yourself now in your notebook. Okay, ket 0 0 we will get, and then f of 0 times 0 0, right? And then you will what you will do, you can write it 0 1 is equal to f of 0 0 0 plus 1 minus f of 0 0 1. Okay, so this is for the, so both are done. Okay, so now we are going to apply uf. Now we are going to apply uf to this one, the third one, right? And then we will be applying to the fourth one, right? 1 0 and 1 1. So let us do that. Let us do that. That is also very easy, right? That also should not be very difficult, right? Uf applied to 1 0, which is equal to, again, use the formula 1 comma 0 XORed with f of 1. This time it is f of 1 because x is 1, right? Again, xy. Okay, xy, the formula. If you know that formula, you can do everything. That's the formula of the generalized formula, as I told you about this uf. Okay, uf application. So if you remember that, then everything, then it is very easy. Okay, if 0, okay, then what will happen? So f1 is equal to 0. So again, for both the output results, we can have 1 0 is equal to 1 0, which is equal to 1 minus f of 1 1 0. Okay, so if you know the first uf applied to ket 0 0 calculation, if you know, the other ones are straightforward. And similarly, f of 1 is equal to 1, then we are going to have uf 1 0 is equal to 1 1, which is equal to f of 1 times 1 1, and therefore now you can write it as uf 1 0 is equal to 1 minus f of 1 1 0 ket 1 0 plus f of 1 1 1. Okay, so this is the result. And remember, like, we are solving it sequentially, like, one by one for our understanding. But remember, when the oracle is actually applied to all these state, all these calculations are happening simultaneously inside the algorithm. Okay, that's the beauty of quantum computing, right? So you will be like, this is very surprising to the, like, those who are new to this field. This is very surprising to them, that how is it possible? But this is what is happening. All these calculations which we are doing by hand, this is actually happening simultaneously, like all together, and also very fast at the same time. Why fast? Because of superposition, because of quantum parallelism, which we discussed yesterday. Okay, so remember, we are solving it one by one for our understanding, but it is actually happening very fast internally and also simultaneously because of superposition. So uf ket 1 1 is equal to 1 and 1 XORed with f of 1. Okay, so this is the final one, and then after that we will be able to move to step 3. Okay, so again, like, you can do the calculations now. So since you are familiar now, take f1 is 0, then you are going to have uf 1 1 is equal to 1 1 is equal to 1 minus f of 1, and then 1 1. Okay, and then if f of 1 is equal to 1, then so let me see, somebody is joining, I have to check. Okay, ma'am is joining. Okay, then what will happen then? Uf of 1 1 is equal to 1 0 is equal to f of 1 times get 1 0. Okay, and now therefore what we will get, what we are going to get, uf applied to 1 1 is equal to f of 1 1 0 plus 1 minus f of 1 1 1. Okay, now by solving all this, so therefore what will be ket phi 2? We are going to solve ket phi 2, right? So we will have, because we need the state after the oracle, right? Because from that only we can then derive, apply Hadamard gate, and then find out step 3. So we will have ket phi 2 is equal to, what is ket phi 2? It is uf applied to ket phi 1, right? And ket phi 1 was what? So basically half uf applied to ket 0 0 minus uf applied to ket 0 1 plus uf applied to 1 0 minus uf applied to 1 1. Okay, that is the one, right? Uf applied to ket 5. So uf applied to all the states simultaneously because of the superposition. So this is what I was meaning. And now we have all the values for all these stuff, right? Uf applied to ket 0 0 we have solved. Uf applied to ket 0 1 is solved. So just put those values here. So ket phi 2 is equal to uf applied to ket phi 1, and then start putting the values 1 by 2. Okay, once you start putting the values, then you are going to get this result. Okay, I'm going to write the result directly. You can solve it. It is it's not very difficult. Okay, you should be able to solve it easily. 0 0, this is the result which you are going to achieve. Then 1 minus 2 f of 0 times 0 1 plus 1 minus 2 f of 1 times 1 0, and minus, I'm going to write it here because of the lack of space, 1 minus 2 f of 1 1 1. Okay, this is the result which you get phi 2 generalized result after applying the oracle. And now into this result, we are going to apply what? We are going to apply the Hadamard and identity operation, right? Identity, because in second qubit we are not doing anything, right? So therefore it is h tensor I, as I have mentioned you yesterday. It is h tensor I, right? So let us start applying the step 3 into step 2 into ket phi 2, right? So step 3 will be apply Hadamard gate to so we perform the operation h tensor I, right? So just have a look at the circuit, and just check for yourself that it is H tensor I, right? Because H is the first qubit. Hadamard is applied in the first qubit in the third step. Okay, after third step we are getting this result, and then I is the second one, right? Because we are not doing anything to the second, and not doing anything means applying identity, right? It is equivalent to applying identity. Therefore, we are going to do H tensor I to the get phi 2. That means the state which we received after applying the oracle. So again, we will do the same thing. We will take each of these terms. Okay, we are going to take each of these terms. If you see, I'm underlining them, each of these term, and we are going to separately apply H tensor I to them. But please remember that it's all happening simultaneously. Okay, we are going to do it separately for our analysis because it is easy to understand. So therefore, for the first step, H tensor I, we are going to do 1 minus 2 f of 0 divide by 2. So just taking the factor out, and 0 0, which is equal to 1 minus 2 f of 0. This is the coefficient which we took out, because remember outside also there is a half, right? So this half, like, you will get multiplied, right? Will get multiplied with all the terms inside. So I'm just taking the considering that half as well. And then I applied the, so Hadamard tensor, right? So therefore, like, this is the first qubit, this is the second qubit. So therefore I applied the Hadamard to the first qubit, and you will get ket 0 plus ket 1 divided by root 2, right? And second qubit is left as it is. Okay, very simple, right? And then 1 minus 2 f of 0 divided by 2 root 2, and then you just need to tensor them together. So once you tensor them together, it will become ket 0 0 plus ket 1 0. Okay, now in a similar way we are going to do it, and now you can also do it by yourself. Again, in your notebooks you can start calculating H tensor I, and then 1 minus 2 f of 0 divided by 2 for 0 1. Okay, so therefore again, like, you will take the coefficient 1 minus 2 f of 0 divided by 2, and then apply the Hadamard gate to the first qubit, which will again give you ket 0 plus ket 1 divided by root 2, right? And second qubit is 1, so that is left as it is because identity is applied onto that. So identity does nothing. And then 1 minus 2 f of 0 divided by 2 root 2, and then again tensor them together. So you will have ket 0 1 plus ket 1 1. Then next one, so H tensor I applied to 1 minus 2 f of 1 divided by 2 1 0, which is equal to 1 minus 2 f of 1 divided by 2, and then again Hadamard applied to ket 1 state. Remember, ket 0 minus ket 1 divided by root 2, and then second qubit is not done anything, and then we finally write the results 1 minus 2 f of 1 divided by 2 root 2, and then ket 0 0 minus ket 1 0. And similarly, now the next one will be, the last one will be Hadamard tensored I 1 minus 2 f of 1 divided by 2, and then we have the state kit 1 1 this time. So again we will have 1 minus 2 f of 1 divided by 2. Hadamard applied to ket 1 is ket 0 minus ket 1 divided by root 2, and then second qubit is also ket 1, right? So but we don't do anything to that, it's identity. Okay, H tensor I. Okay, so therefore 1 minus 2 f of 1 divided by 2 root 2, and then finally we get 0 1 minus 1 1. Okay, so therefore these are the states, and therefore now what we are going to do, we are going to assimilate them together. Okay, so once we assimilate them, then what will be the result? With some simple algebraic manipulation, so with some simple algebraic manipulations, okay, with some simple algebraic manipulations, the final output state output state get phi 3 is, therefore get phi 3 will be, get phi 3 is equal to, what was it, h tensor I applied to get phi 2, right? And all the calculations which we done above, again please remember, are happening simultaneously. So therefore with some algebraic manipulations and by assimilating all the results together, you are going to get this result, 1 minus f of 0 minus f of 1 as a coefficient, and then get 0 and get 0 minus get 1 divided by root 2 plus f of 1 minus f of 0 as the coefficient, and then get 1 get 0 minus get 1 divided by root 2. So basically it is trying to say that you are going to have 0 and 1. So this is the first qubit. Okay, this is the first qubit, and in this is the second qubit. Okay, what is this state in this is the second qubit. Okay, and what is this state? This is the minus state, right? Get 0 minus get 1 divided by root 2, what is that? Get minus, right? And get 0 plus get 1 divided by root 2, what is that? Get plus, right? Get, we have these shortcut notations for them, right? Because every time you do not want to write like, such a big expression, right? Therefore you have to denote it some with some notation. So therefore we use get plus and get minus, right? These are also the diagonal states, right? In the block sphere, right? It is in the x basis, in the x axis basis. Okay, and then so again this is also the first qubit, and again this is second qubit, which is minus state. Okay, and now with this, therefore we are now ready to apply measurement. Okay, we have received ket phi 3, and now into the ket phi 3 we are going to apply measurement, and measurement is going to collapse this state. Okay, how will the collapse happen? Now we are going to see. Okay, for the constant and balance cases, how will the collapse of the quantum state happen? Look at this state. This is quite big one, right? It's quite a big one, but remember we are ignoring second qubit. So we are actually not measuring second qubit. Remember that. We are only measuring the first qubit. Okay. So therefore we will be only worried about the first qubit and its coefficient as well. The coefficient is for both, of course, but we are only going to worry about it for the first qubit because we are taking measurement for the first qubit only. So step 4. Step 4 will be measurement of the first qubit, right? Measurement of the first qubit is performed. Then what will you get? Let us start calculating for f is constant and f is balanced. Okay, let us take the, because what is the ultimate goal? To find out whether the unknown oracle function is a constant or a balanced. Okay, that is the ultimate goal, right? Remember the ultimate goal. So if f is constant, then we said in the XOR, in a compact way, we said yesterday that f of 0 XORed with f of 1 is equal to 0. That means the outputs are constant regardless of the inputs. Okay, So therefore, now let us start calculating. Okay, so if let us say, like, we were having two conditions. If you recall, we were having two conditions. So we defined f0 and f1. If you recall, yesterday we defined that table in the very very beginning of the class. I defined a table where I defined f0 f1 and f2 f3. So we are now going to check for both of them, okay, because those both were constants, right? So now we are going to check for both of them. How will you check for both of them? So f of 0 is equal to f of 1 is equal to 0. Okay, this is what you got for f0. So what will you get then? Now you are going to put these values, f of 0, f of 1, here. Look here, look at this expression here. Put those values here. Okay, phi 3, right? You will put here, right? Because only till the first qubit, second qubit we are not measuring, so forget that minus state, forget that minus that it exists. We have forgotten it already. Only be concerned about the coefficient associated with the first qubit. Only think about that. You are going to now put those values, f of 0 is equal to f of 1 is equal to 0, into that expression, and then what you are going to find out is ket phi 3 will be equal to ket 0 and minus state. Okay, you are going to find that it is ket 0 and ket minus state, and similarly for f of 0 is equal to f of 1 is equal to 1. So this is the f1 function which we defined yesterday. You are going to find out ket phi 3 is equal to minus of ket 0 and minus. Okay, therefore from these two results we can say that ket phi 3 is equal to plus minus ket 0, because plus result has also come, minus has also come, right? So therefore you can write it plus minus together, right? It's a shortcut notation we use in mathematics, right? Plus minus ket 0, and therefore what will be ket phi 4, what will be the collapse? Therefore the state collapses to ket 0, because you take the measurement of only the first qubit. Second, this is the second qubit. You have already forgotten second qubit, right? So why to worry about that? Now, regardless of the amplitude value, whether plus or whether minus, you are only concerned about the state, the output result, algorithm output. Remember, yesterday I told you what is algorithm output. When I was giving you the definition of F0 XORed with F1, at that time I told algorithm output. So now you can connect that idea here. Okay. So try to connect the idea which we studied yesterday. Algorithm output. This is the algorithm output. Okay. This is the algo output which I taught you yesterday. Okay, and it indeed comes out to be ket 0. That means the function is constant. Okay, the function is constant. So this is a way of verifying. Okay, now you already know that whenever the function is 0, whenever the output is 0, therefore the or unknown function in the oracle is a constant function. A similar analysis can be done for balanced also, right? So if f is balanced, okay, f of 0 XORed with f of 1 is equal to 1. Okay, this will be for which one? This will be for, remember, f2 and f3. Just from your previous notes, recall f2 and f3 in the very beginning of the yesterday's class. Okay, so we are going to now take them. F of 0. So let us start with f2. Okay, f of 0 is equal to 0 and f of 1 is equal to 1, right? So input changes, output changes basically. And then again calculate ket phi 3, again put that into above expression, ket phi 3 expression. You are always going to get this state. And similarly for f of 0 is equal to 1 and f of 1 is equal to 0, you are going to get ket phi 3 is equal to minus 1, and here the result of second qubit is also there. So ket phi 3 will be equal to plus minus get 1 get minus, and once you take the measurement it collapses to, and you only measure the first qubit, remember, so it collapses to the state 1 get 1. Okay, so therefore this concludes the proof of Deutsch's algorithm, and now you can connect all the ideas together and you can see how with this circuit analysis, with the generic circuit analysis, we are able to prove for all the functions which we defined in yesterday's class, f0, f1, f2, f3, how all those results come into the picture, and therefore how those oracles. So now we have to check whether those oracles are valid or not, which we have defined yesterday. And for that, we are now going to go to the we are now going to go to the Qiskit textbook of this. So let us check the Qiskit textbook. So this is the Qiskit textbook of Deutsch algorithm. So we have completed our theoretical analysis. We verified all the results. We derived the whole circuit step by step. And I hope that there are no doubts, because it's very simple and it's very easy also. And if you like, since you all are familiar now with the multi-qubits, etc., and their analysis, if you know the circuit analysis of multi-qubits, then it is quite easy to follow and not very difficult. And now what we are but also you have to remember, like, all those calculations are happening simultaneously each side. Okay, so they do not happen sequentially. We have done it sequentially, we cannot do it parallelly. So why we have done it sequentially, to check for the results, to understand how they are happening. Now let us go Deutsch algorithm with Qiskit. Let us see how that works, and then we will start a little bit with Deutsch Jozsa. So so sorry, so first of all, like, we are what we are going to do is that we are going to import the necessary libraries, right? So from Qiskit we import quantum circuit, we take AER and execute, right? And as you all are familiar, these are the things which we require, right, to make a quantum circuit. So we can define a quantum circuit, we need the AER to simulate, etc., and then execute is for the running of the circuit, etc., on the simulator. Okay, you're already familiar. And then plot histogram also is very self-explanatory name, right? I mean, it's a self-explanatory name. So most of the functions in Qiskit are self-explanatory names. Okay, that's how function definition should be, right? That is how we define functions in computer science. The name of the function itself should be very intuitive and self-explanatory. Okay, that's a good coding practice. Okay, anyways, let us not go into that. That's software engineering. Constant oracle. So let us take the help of constant oracles. Oracle with identity gates. Okay, now we are going to implement Deutsch's algorithm for a constant function. So here, as you know, we are going to measure only one qubit. So therefore, in we have two qubits. Okay, but classical bit we have only taken to be one, right? Why? Because we are only going to measure only the first qubit, right? You're not going to measure all the qubits. So that's why you take it as one. Okay, and then you name the circuit as QC. You can name it something else also. Okay, it's completely your choice. You can, anyway, anything you can, whatever name you like, you can name it. Okay, then place the second qubit in state 1, right? That's the first step, right? Because remember, from the steps, go back to your steps. Circuit analysis, the circuit starts from where? Ket 0, ket 1, right? By default in Qiskit, the state is already in ket 0, so therefore you don't have to do anything to the first qubit. But the second qubit is already also in ket 0, so you have to flip it, right? You have to flip it and get it back to ket 1, right? Then only you will have ket 0 and ket 1 in the bottom, right? So that's why we are doing that. Okay, very simple. Then we apply Hadamard's to both the qubits. Very simple operation, right? We apply, this is the first qubit, this is the second qubit, right? Very easy. And then we keep putting the barrier also, like, just for our it's like putting the barrier makes the circuit, like, look neat, basically, just like how I was putting barriers while doing the quantum circuit analysis with you. Okay, just like we put barriers here, right? So if you go here, like, what are these lines? These are barriers only, right? And these barriers helped you analyze the circuit result at each step, right? Step 0 is this, step 1 is this, right? Step 1 is this, after applying Hadamard we get this, after applying Oracle step 2 we get this result in the finally this large state. Okay, step 3 and so on, right? So this helps you, this barriers. Okay, so it also also it is representation wise is also it is very good. And then we create the constant oracle. So first of all we are creating the oracle with the identity gate. So basically actually we are doing this one. So let us go. So we are verifying this one, identity gates, this one. Okay, first one, here my cursor, look at my cursor, first one. Okay, and then what we do, we put a header mud to the first qubit. Okay, then we are going to put a header mud. So this is the circuit which you are going to have. We put a header mud on the first qubit, very very easy, you can see. Okay, this is the uf part. Okay, this is for what we are like doing all the calculation. We did a generalized calculation, but you can do a calculation for this circuit as well manually with hand. That also you can do, it should not be that much difficult. Okay, and then we apply Hadamard, we apply UF, and then we apply Hadamard to the first qubit. So here nothing is applied, so that's why we wrote Hadamard tensor I, right? Identity. Okay, nothing. You can also put identity also if you like, but no need to put because you already know that nothing is applied. I could have also skipped this applying identity. It would have been completely blank, but it will not look that much efficient. So that's why I put this identity gates. But actually, you can remove them, and it's the same thing. Okay, so and then you measure the first qubit. Okay, so this circuit is very similar to what we have analyzed just now. Okay, so you can see how it matches. So this is what you need to do, right? Like whatever there is in theory, you should try to implement the similar kind of thing in practical also, and verify that whether it really works or not. And then you measure the zeroth qubit, the first qubit to the zeroth classical bit, because you have only one, right? I mean, we have only defined one because we only need to measure the first qubit. If we define two, that means we have the option of measuring the second as well. But that's not part of the algorithm. Second qubit has the ket minus state here. Okay, so the ket minus state. We don't need that. Okay. Now, then we use this code you are already familiar with. So I'm not going to go through it just like very briefly. So we define our backend. So basically our simulator, you can take AER or Quasar or anything. Both the simulators operate the same way. And then you execute the circuit on the simulator. So basically taking your circuit QC and executing it on the backend. Backend is what? Your simulator. For how many times? For 1,000 times, right? Because you have to run the circuit many times, right? Why is that? Why you have to run the circuit many times? Because the results of quantum computation are probabilistic in nature, right? As we have already seen, we have coefficients attached with the quantum states, and you do not know that what states like what will happen after the measurement, like where the states will be collapsing to, right? So therefore you count those, count those occurrences of those states. Okay, so let's say you have ket 0 plus ket 1 divided by root 2, right? Which is the ket plus state. Okay, and you know that 1 by root 2, 1 by root 2 is it is associated as the coefficient with ket 0 also, ket 1 also. Therefore, like whenever you take measurement, sometimes it will appear ket 0, sometimes it will appear ket 1. So we count all those and we observe that, with the coefficient which is associated with that quantum state, if we take the absolute value of that, we get that much number of results. That means 1 by root 2 absolute value squared is what? Half, right? So half of the time we get ket 0 as measurement, and half of the time we get ket 1. So basically we we run the circuit many times, we collect all the occurrences, and after collecting all the occurrences, we try to find out how many times that particular state appeared. So for the Hadamard, ket 0 plus ket 1 divided by root 2, ket 0 appears approximately 50% time, and ket 1 appears approximately 50% time. And the similar way, all the other circuits will also give you a probabilistic result like this after measurement. So that is the meaning of shots. Okay, just running it and collecting all the occurrences. This is all happening internally. Okay, remember, like I'm not doing it here, but this all happens internally. Then what you are going to get, then you are going to extract the result from the execution. Okay, so you have executed the circuit here, then you are going to extract the result from the execution, because I mean you have to extract the result, right? I mean you have executed the circuit and stored it in a variable, then from that variable, with the help of that variable, you need to extract the result, right? Because then only you can see the counts means what? Those occurrences which I was talking about. That is the meaning of counts, right? And that is like, with the counts only, that is where you have stored, like, how many times a particular quantum state appeared after each circuit run. Okay, so 1,000 shots mean this whole circuit is going to run 1,000 times internally. Okay, so that's it feels like a lot, but it is not actually. It happens very quickly given the speed of our classical computers. I mean, they are also matured enough right now, so yes, you can do all these stuff. And then what you do is that then you get the counts from the circuit, print it. Okay, it's again like, if you don't want to print, you can, like, skip it. But yeah, if you want to print, then good, it's a good information, you can print it. And then you can plot the histogram. Okay, and for the histogram, you can see that zero is appearing 100% times. And we also saw that in the theoretical analysis, that zero is supposed to happen 100% times. Here we saw. Okay, get 0, can you see 5 4 as get 0 for constant? So that's very obvious, right? It should be. But we are verifying the oracles, remember. This is our first oracle, right? We are verifying it. So remember, now we are going to verify the second oracle, right? What is the second oracle? Identity and X gate, right? So let us do that. What will be there? So oracle with X gate on the second qubit. Okay, so again, the circuit is very same. Not much is different, only the oracle here it is different. Okay, there were two identities earlier, now it has been on the second qubit we have applied the X gate. Okay, so you can see the circuit construction is very straightforward. Once you know the gates, you just need to put it in the oracle, and this is how it will look like. So this is the oracle for this one. Here by cursor, this one. Okay, and then header part, and then measurement. So once you do that, then again you are expected to get 0, because algorithm output 0 means constant. So again we verified that yes, indeed that oracle which we defined yesterday is a constant oracle. Okay, so these are all we are verifying practically. Then for balanced oracle, we defined the third one. This is the third one, right? This is the balanced oracle, right? This one. We are now going to verify that. Okay, so again, the circuit is same, but here now we put the CX gate, right? The C naught gate with the controlled as 0 and target as 1. But you can do it in opposite way also. I would recommend that you do it in opposite way and check what kind of results are you getting. Okay, you can do it in any way. Okay, opposite means you can make the control 1 and the target 0 also, right? Opposite C naught gate, right? I mean, just flip it. Basically, this target will become the first qubit and this control will become second qubit. That is also possible. Okay, so try doing it. uh, like, in your free time, whenever you are playing with Qiskit, you can try doing these kinds of stuff and check what is happening. Okay, and then you apply the Hadamard, and then what you are going to see is the state. What is the state? You are going to see ket1, right? Because we have already seen that you should see ket1, right? 5 4 is equal to ket1 for balanced oracle. Okay, so we are verifying them one by one, right? And similarly, the last one also very easy, CX with an X gate. So we apply the C naught gate and the X gate on the second qubit, right? We did it here. So C naught gate and the X gate in the second qubit, that is also balanced. And there also we apply that, we put the Hadamard, measure it. This is the circuit, very easy. And then we do the same. This code remains the same. Okay, so that's why I'm not explaining it. This is the same code from even your previous classes also. So maybe you can have a look at that code if you do not recall it completely. And then finally you get one state. Okay, also 100% time. So therefore this proves that all the oracles which we have, they are indeed constant and balanced in their own ways. And now what you can do is that you can form some complex kind of circuit. Maybe you can start putting some other kind of gates. Let's say, like, you put some, like, y gate and z gate, etc., etc. Like, you can put all these things in the oracle, like make a complex oracle, and then try to see what is the result which you are getting. Okay, So this is the Deutsch algorithm with Qiskit. So are there any doubts with this?
No, sir, no doubts.
No doubts, ma'am. That is all clear, right?
Yeah, it's clear.
It is easy to implement, ma'am, right?
Yeah, it's
Simple implementation of quantum gates, right? And in a step by step manner, as we have carried out in our theoretical analysis, right?
yes, yes, no doubts.
Okay, that's great to hear, Roshan. Yeah, thanks for confirmation. So okay, so therefore, since this is clear, so let us move ahead. Let us move ahead a little bit and study a little bit of Deutsch Jozsa. Okay, Deutsch Jozsa is not very large. It is, but before I start Deutsch Jozsa, I need to define a few concepts of Hadamard. So let me start here. Let me first define a few concepts of Hadamard applied to n qubits, because now we are going to use these concepts. Okay, now we are going to generalize the Hadamard gate applied to n qubits. So till now we have applied Hadamard to 2 qubits. But what will happen if we apply Hadamard to all the 3 qubits, all the 4 qubits, all the 5 up to n, where n is let's say 100 also? What will apply? What will be the output if you, let's say, apply Hadamard to all the 100 qubits? Okay, we are going to find the general expression for that right now. Okay, I'm going to directly give it. We are going to take the help of the 2 qubit case and then generalize it. Okay, so Hadamard, this is very important because I am going to directly use these expression in Deutsch Jozsa algorithm, because Deutsch Jozsa will now go towards n qubit case. It's, if you remember, as I told you before, it's a generalization of Deutsch algorithm. Okay, so Deutsch algorithm was simple 2 qubits, but now Deutsch Jozsa will be n qubits. So what will happen if you have n qubits? So that means lot of qubits. So let us start seeing that. So Hadamard applied to n qubits. Okay, Hadamard applied to n qubits. Let us start with Hadamard applied to 2 qubits. Okay, so how do you write that? So Hadamard applied to 2 qubits. Okay, this is also another type of expression, right? I mean, this is same as like Hadamard tensor Hadamard. Okay, Hadamard to the power tensor 2 means applied to 2 qubits. Like if it is 3, then 3 qubits, etc., like, you know, and so on. So Hadamard applied to, let's say, K00 is equal to, what will be the compact expression for that? So the compact expression will be half summation x is equal to 0 to 3 get x. Okay, okay, and those you are not familiar, you can calculate this. So what will be the calculation? So take half, so something like this, half, and then what is going to happen? Summation x goes from 0 to 3. That means you are going to put all these values into the x. So basically it says get 0 plus get 1 plus get 2 up to 3, right? 0 1 2 3. Okay, up to 3, right? And then, so what are these values? These are the same. This is written in the decimal format, but again, as you know already, there is a binary. You can write it in the binary format, and you have already seen this. Okay, 0 is what? 0 0, right? Plus 1 is 0 1, plus 2 is 1 0, plus 3 is 1 1. Okay, so this is the result which you get, and you have already seen this result just now in Deutsch algorithm. Also, the signs were a little bit different. The reason, because we didn't started with ket 0 0 state, we started with ket 0 1 state, right, in the Deutsch algorithm. So that's why you were seeing some sign changes, because remember, whenever Hadamard is applied to ket 1, there is a sign change, right? So that's why you were seeing those sign changes. But yes, anyways, I mean that is understandable. But now this is Hadamard applied to both the qubits where they are started with kit 00. Okay, and this is the result which you get. Okay, now what will happen if you have Hadamard applied to, again, the generic expression? What will happen if you have Hadamard applied to kit 01? So I want to write the generic expression. So how will I write? So Hadamard tensor to, okay, to kit 01, something which we used in Deutsch algorithm. Okay, that will be equal to half, again, summation. And these compact expressions are important to write because every time you cannot write it fully. Okay, so like, that's very inconvenient, therefore these compact expressions help you at that time. Okay, and that is what we are going to use in all the algorithms. Okay, so x is equal to 0 to 3, and then minus 1 to the power x, get x. Okay, when you have the, this is like having the last qubit, has the last qubit defined to 1. Okay, last qubit is defined to 1 and all the other qubits are 0. Okay, so we are going to see the general one also, but this is the formula. And once you expand this, actually you are going to get the same result which you got for the Deutsch algorithm step. So basically this result, okay, which you have here, you are going to get this expression. Okay, you are going to get this one, ket phi 1. Basically you are going to get the expression of ket phi 1. Okay, once we expand this. Okay, I'm not going to expand it, but once we expand it, you are going to get the expression of ket phi 1. Now for for n qubits, what will happen? Now let us start generalizing for n qubits. Okay, the expression looks very similar to what we have seen above, h tensor n, right? Now it is n qubits. N can be defined by u. Okay, it can be 3, 4, anything. But as you increase the n, the expression also increases. So therefore at a certain point after 3 it will be difficult to write. So for n 4, 5, like, it will be a lot of terms, right? Because it is 2 to the power, it increases as exponentially, right? 2 square, like 2 qubits has 4 terms, and then 3 qubits will have 8, right? 2 cube. And then 2 to the power 4 will be 16 terms, right? Then 2 to the power 5 will be 32. So that's a lot of terms to write. So that is why, because to deal with those higher number of qubits and, like, to deal with those kinds of expression, we need these compact expressions, okay, for algorithmic analysis. So h tensor n applied to all 0 qubits. Remember, all the qubits are 0, 0. Okay, and we are going to get h tensored n, and you can write it in this format, 0 tensored n. Okay, again another shortcut way of writing all zeros. Okay, and then what will be the result? The result which you get is 1 under root 2 to the n summation x starts from 0 to 2 to the power n minus 1, get x. Okay, very similar, but replaced with 2 to the n. That's it. Okay, 2 to the n, as I explained you just now, it increases exponentially, right? 2 square is 4 terms, then 2 cube is 8 terms, 2 to the power 4 16, and so on. Okay, so in similar way you can do the expression for 3 qubits, up to 3 or 4, maybe 4 qubits also. But again, 4 qubits also has 16 terms. So yeah, like, you can do it. Definitely it's doable. It will take time, but it is doable. But we don't do that because that is the reason, because it takes time. That's why we need compact expressions. So these are the compact expressions. Okay, now let us take a look at and also, yeah, this is so yes. Okay, so then let us also take a look when the last qubit is 1, right? So the last qubit is 1. So 0, 0, and last qubit is 1, and all the others are 0. What will happen? H tensor n and gate 0 goes up to tensor n minus 1, right? It will go up to n minus 1, right? Because Because why? Because the nth qubit is what? The nth qubit is ket1. Okay, the nth qubit is ket1. So this is the nth qubit, right? This is the nth qubit. Okay, so basically here I can write, okay, this is the nth qubit. Okay, and then this is n minus 1, then this is n minus 2, and so on. Okay, up to 0, like that. Okay, so 0, 1, 2, 3, up to n, and where the nth qubit, the last qubit, is 1, and then n minus 1, n minus 2, like, if you go uh, backward, basically. Okay, so, and again, like, this expression is very similar to what we saw for Hadamard applied to two qubits, where the last state was ket1, first state was ket0. What will be the expression? 1 under root 2 to the n, and again summation, the same, x is 0, 2 to the n minus 1, then minus 1 x, and then get x. Okay, is this correct? So this is same as we have seen in this expression, this one. So remember this expression. This is the expression which we saw, right? Just now we saw this expression, and similar way now we have seen this expression. So going to going to box them, okay, because these are important compact expressions. Okay, okay, so I'm going boxing them. So you see, okay, very, very important. This is very important because we are going to use this now in the algorithm. Now in binary notation, this is for the 2 to the power n is written in the decimal notation, as you saw here. I wrote it in the decimal format first. So this was the decimal format, but this is the binary format. Okay. So similarly for n qubits, this is the decimal format. Okay. And now let us see for n qubits binary format. Okay. Or binary notation. Again, h tensored n, all zeros, and then h tensor n, get 0 tensored n, that will be 1 by 2 to the n summation. And now we are going to write in binary. So how do you write in binary? Y belongs to 0, 1, n. Okay, y belongs to 0, 1, n, right? Because binary, remember, no decimals. There is no decimal. Okay, 0, 1, 2, 3, 4. What are these numbers? These are decimal, right? But we are talking about binary numbers, which are only in 0 and 1, and therefore 0, 1 to the power n, because whenever you set the power, then you are going to get results. So for example, 0, 1, and let's say n is 1. Okay, so let's say the power is 1. Okay, so what will happen? What will be the values which you will get? Okay, you are going to get what? 0 comma 1, because also remember, like, 2 to the power 1 is equal to 2 also, right? So that also. And then what will happen? 0 comma 1, 2. So you are going to get 2 square, 4 results, right? So what are those 4 results? You already know: 0, 0, 0, 1, 1, 0, 1, 1, right? And similarly you can also go for 0, 1, 3, right? Which will give you 0, 0, 0, 0, 0, 1, 0 1 0 0 1 1 and so on, okay, up to 1 1 1, right? Because this is 2 square is 4, then 2 cube is 8, so this will have 8. Okay, are you getting the part? Very very simple. This is okay. This is not very difficult. Okay, do not stress too much on this. Okay, it's very very simple. Just have a look. It is very very, it makes, it's compact notation. Okay, many people get scared by looking at these mathematical expression, but try to understand them in a, like, like break them into parts and then understand, like, put n, like, have some values of n. Let's say you start with n is equal to 1 and go up to n is equal to 3, then you will automatically understand how the expression is generalizing. Okay, so that is the way of understanding these expressions. And then get y, this get y should not forget, this is in the binary format. Okay, now what will happen if you have, if you have a general state? Okay, if you want to apply Hadamard to a general state, so let us also see that. So Hadamard tensored n to a general state, so let's say get x. Okay, not a 0, not a 1, nothing, just a general state, get x. And again, 1 upon 2 to the n summation y belongs to 0 1 n minus 1 x dot y. Okay, means multiplied basically, and then get y. Okay, so these expressions are very 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 important. So again, I am going to box them, and maybe you should also, I also recommend you that you also box them in your notebook, because these are very important expressions. And many times, of course, like, you cannot write, you cannot write all the terms, right? Get 0 0 plus for 2 qubit, 3 qubit, it's fine. Even for 3 qubits, people don't write because there are 8 terms, remember, right? So that is why people will not write, okay, for that much number of terms. So that is why what they are going to do, they are going to use these expressions to define. And now, with the knowledge of these expression, now we are ready to see how Deutsch Jozsa actually works. Because in Deutsch Jozsa's quantum circuit analysis, we are going to use these expressions. Okay, remember, Deutsch Jozsa is for n qubits. Okay, so now we are actually increasing the number of qubits, and n is basically starting from 2. Okay, so basically from 2 3 4 5 7 8 10, I don't know how many, like, okay, up till your the quantum simulator limit of 32 qubits or something. Okay, yeah, anyway, so for that, okay, so let us now see what will happen to Deutsch Jozsa algorithm. Okay, so have you all written these expressions? So have you all written the expressions?
Noted, sir. Noted. You.
Okay, please note them down, ma'am. Where, which one you have missed, this one or the this one?
Noted, sir.
Okay, 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 great. So then now we can go for Deutsch Jozsa algorithm. Okay, Deutsch Jozsa. And again, in a similar way, it is a straightforward, as I have mentioned you before, it is a straightforward generalization of the problem solved by the Deutsch algorithm. So Deutsch algorithm for was 2 qubits, okay, but now we are going to extend to n qubits. Okay, so the Deutsch Jozsa algorithm is a straightforward generalization of the problem solved by the Deutsch algorithm. Okay, so it is a straightforward generalization. Okay, and now some points about this. So the algorithm has the same structure. Okay, so this is the first point. The algorithm has the same structure, and is second point is important. Okay, please note it down. This is important. The algorithm has the same structure. Okay, it is similar to the Deutsch algorithm which we have seen just now. Okay, and again, this algorithm allows us to determine this algorithm allows us to determine whether whether a function f of x is constant. Okay, so the criteria is same, only we are again trying to find out constant and balance. It's the same criteria, constant or balanced. But this time but this time what will happen, but this time the function has multiple input values. Okay, in the Deutsch algorithm case, and this is the important point, in the Deutsch algorithm case we are not having multiple input values, right? We were having only one input value, and the second qubit was a supporting qubit, right, helping us in quantum interference and parallelism, etc. Okay, here also we will have that qubit. Okay, that one qubit we will have which will support all the other multiple qubits. Okay, so it will get more clear. Okay, like the function has the function has multiple input values. Okay, therefore if you see this here, in this case in this case although there are functions which are neither constant nor balanced. Okay, so there is another possibility also in this case. Okay, not in the Deutsch, but here in Deutsch Jozsa, since we are generalizing it, we also have a third possibility where the function is neither constant nor balanced. Okay, we didn't imagine that before. Okay, but now we have to do that. Okay, but we are not going to check all those. We are going to see simple constant or balanced cases. But again, if you try analysis with your own oracles, then you will be able to find any of those functions which are neither constant nor balanced. Okay, but we will not consider such cases here. Okay, so example, so for example, so eg, okay, eg for 2 qubit for 2 qubit input. bit strings will be bit strings. Okay, can be, what are bit strings? All those, like, those states which you define, like 0001, those are bit strings, right? Bit strings can be 00011011. Okay, these are, this is for 2 qubit, right? I mean, you already know this. Okay, you can put ket also. I have not put, but yeah, I mean, you can put it. That's not a big deal. But those are the bit strings, right? So these are the bit strings which you get. Similarly, for 3 qubit, you have 000, then 001, and so on. Okay, so again, we have the same case here. Again, we have the same case. So input is what? Again, we have a unknown Oracle black box for computing an unknown function. Okay, we have a black box for unknown function. If we start with if, okay, but this time remember, in Deutsch algorithm we were starting with 0 1 and goes to 0 1, right? Just turn back your notes. I mean, flip the pages over before and check. F goes from 0 1 to 0 1. Input was 0 1 and output was also in the terms of 0 1, and we have seen that also, right? I mean, we started with input, like, ket 0, ket 1, and then in the output we either get ket 1 or either get ket 0. Ket 0 is uh, the constant and ket 1 is balanced. Similarly here also 0 1, but n qubits, because input is n, as I've defined before. Input is n, and then it goes, and but the output is not n. Output will be 0 1, either 0 or 1 bits. Okay, now again same problem. We try to find out whether it is constant or balanced. Determine whether f is constant or balanced by making queries to f. Okay, determine whether f is constant or balanced. It's the same problem statement which we saw in Deutsch algorithm. This is not different. The difference will come in the inputs. The inputs which we are providing, that will be different. That will be this time what? It will be multiple qubits. So algorithm output is equal to all zeros. So let's say when we have algorithm output as all zeros, then we say it is constant. Otherwise, when it is all ones, it is balanced. Otherwise, it is balanced. And here also we measure only first register. Here also we measure only first register, not first register. I will tell what is first register. So first register will have n qubits. Okay, this is your input n qubits, and this is also first register, or this is also known as input register. Okay, this is also known as the input register. Okay, and this will have n qubits, but you will also have a second register which will have only a single qubit, and that will be your supporting one. Okay, it's very similar to Deutsch algorithm. Remember, I'm going to compare them, do not worry. But first register will have n qubits and second register will have a single qubit. Okay, so total n plus 1 qubits, basically n qubits in the first and plus 1 uh, second register 1 qubit, so n plus 1 total. Now using a classical algorithm, we cannot decide with certainty worst case. Okay, let's say it is worst case certainty whether whether f is constant or balanced using any less than 2 to the n minus 1 and then plus 1 queries. Okay, so what it is trying to say is that for a classical algorithm, it will definitely take 2 to the n minus 1 plus 1 queries sequentially. Remember, this is sequentially. Okay, so therefore sequentially you will require 2 to the at least 2 to the n minus 1 plus 1 queries. So let's say if n is equal to, let's say 2 qubits. Okay, so this will be what then? 2 to the power n minus 1. So 2 to the power 2 minus 1 is 1. So 2 to the power 1. So 2 to the power 1 is 2, and then plus 1 is 3. So therefore, for a multiple qubit Jozsa case, you will require 3 queries. Okay, you are going to require 3 queries, and also you have to put them sequentially. Okay, so you are going to have 3 queries, but again with Deutsch Jozsa you are going to have only a single query. So that means the the property of being constant or balanced is a global property of f. Okay, the property of being constant or balanced is a global property of f. And as for the Deutsch problem, as we saw, a quantum algorithm can take advantage of quantum superposition interference to determine this global property of f. Similarly is the case for Deutsch Jozsa. Okay, so the Deutsch Jozsa algorithm will determine the result making only one query. Remember, for 2 to the n, if you have n as 2 qubits in the first register, then there were 3 queries would require, but still, and similarly you can increase n to whatever number you want, 2 to the power 10 minus 1. Okay, or 2 to the power 11 minus 1 or something. So n is equal to 10 qubits, 11 qubits, and so on. You can increase that. It is going to be a very large number, right? And that much number of queries you have to give sequentially to a CPU to solve the same problem, but with a quantum computer. And this is the real power. Now you can see. Okay, now you can see with this generalization that with multiple number of qubits, Deutsch Jozsa is still able to give you the result in only one query. That means you have to only run the algorithm once and you will get the result. Okay, so that is the look, this is the beauty of quantum computing. Okay, try to conceptualize this. Okay, try to visualize this, how the beauty, what is the beauty of quantum computing, how is it powerful than a classical computer. Absorb these algorithms inside your mind and try to understand how this beauty of quantum computing is coming to the picture, why people have so much of investments going on into quantum computing, why is it such a fruitful field to study. Okay, analyze these things. When you study these algorithms, it gives you hope. Okay, it gives you a hope that yes, indeed this field is revolutionizing. Okay, so this making only one query and provides, and it also provides deterministic exponential speed up. Okay, it gives you a deterministic exponential speed up compared to classical one. So classical one we have seen already, 2 to the power n minus 1 plus 1 queries at least that will be required. But here only one query is required over the classical one. Okay, and now what I'm going to do is that I'm going to define constant and the balanced oracle. Okay, so let us define the constant and the balanced oracle. So how will they look like? Like, just we have defined it for the Deutsch algorithm case. How will it look like for Deutsch Jozsa case? We have to see that, right? If we see that right now, then it will be easy to understand the Qiskit version. So constant oracle. Okay, constant oracle. And let us make a table. Okay, let us make a table. It will be easy to understand. So constant oracle, and then okay, let us do something like this. Like, can have these lines. Okay, what will have in constant oracle? Now try to compare this oracle with the ones which you have studied in Deutsch algorithm. Remember, there are multiple inputs. Okay, so input has no effect on output. Okay, input has no effect on output. Okay, we can therefore we can randomly flip bits. We can randomly flip the qubits. Why? Because remember, in Deutsch Jozsa case, there was one case where there were no qubits, there were no quantum gates applied. Okay, and then in the second case, we were having the X gate applied to second qubit. So we can randomly, keeping that Deutsch algorithm case in mind, we can randomly flip the output. Flip the output qubit. Output qubit means the second register. Okay, output qubit register. Okay, and I'm going to show you by diagram now what it means, like, this input, first register, second register, output, all these things I'm going to show you now. Okay, it will become more clear when we do the circuit analysis. This time the circuit analysis will involve a lot of mathematical expressions, so do not be scared from that. You don't have to rote learn any mathematical expression. Remember, you are not here to rote learn any expression. Okay, you are here to understand what is happening. Okay, even if you don't remember the expression, that's fine. Okay, but understanding is more important. Remember, rote learning is not. Okay, flip the output by applying X gates. Okay, by flipping can only be done by X gates, right? I mean, there are other ways also. Okay, you can use RX gate also for flipping, but let us consider, like, simple cases. Of course, you definitely have other alternatives as well. You have universal quantum gates too, right? So many things are there, but let us take the simple approach, which is easy to understand. But of course, remember, there are other approaches as well. Okay, so and the output, therefore, and what is the algorithm output for the constant oracle? If it is a constant oracle, then the algorithm output will be all zero string. Okay, just like, remember, you were getting like a single zero output in the Deutsch algorithm case, as we saw. So here, since it's multiple qubits, we will see this kind of output. Okay, we are going to see this kind of output. So let us take an example where n is equal to 2 qubits. Okay, so how will the circuit look like? So this is a valid circuit. Okay, And please note down this circuit. So let's say you have 2 qubits in the first register. Okay, so this is a constant oracle. Okay, so this is a constant oracle where this one, these 2 qubits are the input or first register, REG. I'm writing in short. Okay, REG register. And this one, this last one, is called as the output or second register, which is always one. Okay, always one means like which is always a single qubit. Okay, this is always a single qubit. Okay, and remember, in the Deutsch algorithm case, this first register or the input register was having only 1 qubit. Okay, but now the qubit has increased, remember. Okay, and this can go up to n, but the second or the output register, REG register, is always a single qubit. Okay, so this is how I am defining input and output registers, or first or second registers. I will say first or second register because that's much more nicer to understand. Similarly, like what we saw is that we can randomly flip the output qubit. Output qubit means second register qubit. So therefore, this is also a valid constant oracle. This one looks very similar to Deutsch algorithm, right? Only difference is multiple qubits. Okay, this is also a valid constant oracle. Okay, this is also a valid constant oracle. Now, what about balanced oracle? This is also very similar to Deutsch algorithm case. Okay, compare these oracles, okay, which I'm drawing with the oracles which you have drawn in your notebook for Deutsch algorithm. Then it will give you more conceptual clarity, right? Because conceptual clarity is important, right? For studying any subject, this is not only about maths or science. Even if you take any other subject, okay, conceptual clarity is what you should focus on always. Now, then second, perform perform C naught. Okay, this is how you are going to construct. So I'm just writing it in words first, then I'm going to show you the diagram. Perform C naught with register 1. That means register 1, okay, with input. Okay, let me not sorry, input as control and output, that which is register 2, right? Register 2 as target. Okay, what we are going to do, perform C dot, and with this we will be concluding this class, and then again continue in evening 7 to 9. uh, then second point is what will but remember, also this time we have multiple qubits. Okay, and multiple qubits have, like, cases like 0001 1011, right? It's not only like only single 0 or single 1, right? So there are, this is different case. Okay, so therefore for different input values, okay, for different input values, just wrap just wrap. Okay, wrap. Okay, wrap selected controls. Okay, wrap selected controls of input or first register, okay, with x gates. Okay, with what? With x gates. Okay, and output will be what? Output will be all one string. Okay, so therefore it is not a, output is not a all 0 bit string. It is a, it will be, as you will see, it will be a, it will be like a all 1 bit string. Okay, all one, very similar to what you have seen in Deutsch algorithm, right? For one, for balance, 0 for, like, constant, same thing only. Only thing is that, like, you have multiple qubits. Okay, so don't get scared. Now what will be now how will you define the oracles? Okay, so it is, that is interesting. So let us see. So let us take, let's say that the input is, let's say, like, 0 0. So then how will the oracle look like? Okay, how will the oracle look like for input 0 0? Let us see. Okay, so let's say input is 0 0. Okay, so let us say input has, like, 0 0 means two qubits in the input or the first register. Okay, and of course we have the second register as single qubit always by default. Okay, always a single qubit, as we have seen. But it says, but remember what it says. It says perform C naught with input register as control and the output as the target. Okay, input register as control, that means do this input register as control. Remember, these are input. Okay, these are input reg. Okay, as control, and output, that means the second register as the target. That means this perform C naught with input as the control and output as the target. But there is another input, right? There is another qubit, right? This one is also there, right? So we have to do for that also, right? Okay, this is the oracle for input 0 0 when you start with 0 0 here. Okay, 0 0, that is what I mean by 0 0. What will happen if input is 0 1? Input is 0 1. Let us see. Okay, so let me draw, like, I have to draw it in a different way now. Okay, okay, so 0 1, so 0 1, and then you have the third one. Okay, here you have the basically the second register. Okay, 0 1, remember it says for different input values just wrap selected controls of input register with X gate. Okay, means it is saying wherever you have one, wrap that particular control X gate. Okay, wrap it. How you are going to wrap it? So first of all, you are going to not do anything here, but here you are going to wrap it. Okay, here you are going to wrap it. Okay, X gate. Okay, and now you are going to apply your, what you are going to do, you are going to apply your C naught gate. Okay, look at this very carefully. Okay, what I am doing, this is very important to understand the oracle. Okay, this is very important step. Okay, and then X gate, wrap it. Okay, wrapping which one, where the state is 1. Okay, that one I'm wrapping it with X gates. Okay, and this is the, so just like this is the oracle here, this is the oracle. Okay, this is the oracle. Okay, are you getting the point? Wrap the C naught selected controls. Okay, selected controls of input register with X gates. Okay, selected controls means wherever the control, wherever you have the 0 1, second qubit is in 1. So therefore you take that selected control and wrap it with the X gate. And similarly you can also do it for input. Let us also show it for 1 1 as well. Again, this is input register. Okay, input or first register. Okay, therefore now what is going to happen? Now you have 1 1, so therefore you are going to wrap both the controls. Okay, because both are 1 1. Okay, both are 1 1. Okay, let's say this is the, and then also you have this. Okay, and wrap it with X gates. Okay, this is the oracle for, this will be the oracle for input as 1 1. So now you can see with the input values how it is changing. But this second register, it has a single qubit and it is constant. That is also started with ket 1 only, okay, just like Deutsch algorithm. In Deutsch we started the, remember, the lower qubit as ket 1 and the above qubit was ket 0. But now for the multiple qubit case, the above qubits can have other values also apart from ket 0, right? That is why we have to do this technique, okay. But the oracle is very similar, okay. The oracle is very similar. Whenever you have input as a single qubit, okay, then you can put only a c naught gate. So how this oracle resembles, this oracle resembles with this one, this oracle resembles with this circuit balanced. If you see my cursor here, third one, this is how the oracle resembles. And we have now generalized that oracle, okay. This is the generalization of the oracle for the Deutsch Jozsa case. Okay, once we see this in Qiskit, then it will be more clear. Okay, and similarly now, like you can make for input as 1 0 also. We have not tried that, right? So make it for yourself. It will be very similar to 0 1, but which control you should wrap, that you need to see. Okay, and in a very similar way, you can also do it for 3 qubits as well. Okay, so whenever you have 3 qubits, you will be able to do it for 3 qubits as well. Okay, so in that 3 c naughts will be used, right? So just quickly, just if you have like input as 0 0 0, then what you're going to have 3 qubits, and this is the second register, okay, and then controls from each of the qubits, okay, because input first register is control. Remember, this is the input, right? Input or first reg, okay, and then like this, okay, that's it. This is your oracle. Okay, this is input for 3. This input is 3. Okay, start with 0 0 0. And similarly again, like if you have 0 0 1, then here x gate will be put. Okay, if you have 0 0 1, let's say this becomes 1, then here x gate, here x gate. That's it. Just wrap it. Wrap the selected control. Okay. So this is how we do Deutsch Jozsa algorithm. This is to I know that this is a little bit more complex than the Deutsch algorithm. I do agree with that, but if you go through it step by step, then it should make more sense and start comparing it with the Deutsch algorithm case. You will see that it makes more sense to construct the quantum circuit in this manner. Okay, so this is and then now in the evening class, what we are going to do is that we are going to derive the circuit analysis, and we are also going to see the Qiskit version of this circuit as well. Okay, so I'm going to stop presenting, and if you have any doubts, please go ahead. Any doubts?
No doubt, sir.
Okay, is everything clear, ma'am? Is it fine?
Yes, sir. Yes, we'll go through once again by ourselves
Yeah,
and we
yeah.
have the
Please,
back.
yes. Yes, ma'am. Exactly. Yeah. Please go through. Thanks, Roshan, for confirmation. But yes, Roshan, please you also go through them once again whenever you get time. And again, like Deutsch Jozsa is the generalization. So yeah. Okay. Thanks, Roshan. So again, like just to quickly recap in a minute, Deutsch Jozsa is the generalization of Deutsch, and the oracles look very similar to the Deutsch algorithm. The only thing is that we have multiple qubits, we have multiple input values, and that's why the oracle construction is a slightly different and a bit more generalized version of the Deutsch algorithm. In Deutsch, we were only having single qubit, but now in Deutsch Jozsa, we have multiple qubits and we have divided them into registers. We call it first or input register and second or output register, which always has a single qubit, but the other one, the first register, is going to have multiple qubits. Okay, so let us see more of that circuit analysis in the evening. 7 to 9 class is there again. So we are going to see the circuit analysis, complete it, and then we are going to see the Deutsch Jozsa algorithm in experiment in Qiskit.
Sir, is quantum machine learning will be covered in this lecture series, or what's the plan?
Yes, ma'am. Quantum machine learning is not now. Quantum machine learning will be most probably next month end, I think. November end, I think. I have to check the schedule again, but I
Okay.
think most probably it is November end because quantum machine learning is going towards the application part. So we
Mm.
have kept the application part after running through all the essential quantum algorithms, like when students are already familiar with what is quantum phase estimation, Shor's algorithm, Grover, quantum
Mm.
Fourier transform, then variational quantum algorithms. I will only take that lecture, quantum
Okay.
ML and variational quantum. I am only going to take it.
But for quantum machine learning algorithms to work, should we be good with these all quantum algorithms? Is it required or a must, or we can straight away start digging into the quantum neural networks part?
You can start digging into it directly, but if you have knowledge about these algorithms, it is nice actually, because
Okay.
everything builds up in a systematic manner. That is what I believe. So if you
Okay.
have, like, it is good only.
Okay.
Yeah,
Okay.
nothing is going to harm. So, like, this is a way, these are all motivating algorithms and examples, right? And
Yes.
from
Yes.
these, yeah, and from these only quantum machine learning algorithms also emerged.
You must.
So
Yeah.
yeah, that's why, like, knowing these is yeah, not, it's not bad actually. I would say.
Yeah. Yeah. I get it.
But
Thank
yes,
you.
do not worry, I am going to take that class on variational quantum.
Variational quantum circuits and then annealing
Yeah.
computer kind of thing, because the network neural networks are being applied in different types of hardware. So, okay.
Yes, absolutely, absolutely. I'm going to take that web. No need to worry. It will be. I will tell you the schedule also. It should be probably next month only. I think.
Okay.
Yeah.
Okay, sir. Okay, then thank you.
So
Thank
okay, okay, sir. Thank you so much, everyone. So let us conclude here. I'm going to stop the recording.